Welcome to the Hartman quantum tuning fork transport hypothesis, or QTF-Transport for short. This groundbreaking theory, proposed by Colonel James Edward Hartman, explores the possibility of moving macroscopic objects across space, not by pushing them through ordinary geometry, but by using a pair of engineered quantum tuning forks and a special boundary shell. Imagine a world where objects can be handed off between distant locations, emerging as if they've passed through a wall, all while respecting the laws of physics. In this video, we'll break down the core concepts, the scientific motivations, and the speculative mechanics behind this bold hypothesis. The heart of QTF-Transport are two devices, Fork A and Fork B. These aren't ordinary tuning forks, they're precision-engineered quantum resonators, each supporting a set of discrete, quantized modes. When Fork A vibrates in a specific quantum pattern, Fork B, even if located far away, responds with a corresponding pattern. This coupling is more than just a metaphor, it's a physical link, potentially spanning not just space but higher dimensions. The forks are designed to be nearly identical, allowing them to share entangled or correlated quantum states, setting the stage for non-local interactions. To transport an object, it must first be sealed inside a specialized envelope or bubble. This isn't just a container, it's a boundary condition shell, engineered from advanced metamaterials or topological insulators. The envelope isolates the object from its environment, ensuring that all interactions with the outside world are mediated through the quantum fork fields. By tuning its properties, the envelope can couple strongly to the fork's resonant modes, encoding the object's effective state for transfer. This shell is crucial for maintaining coherence and enabling the controlled mapping of the object's state. The core mechanism of QTF-Transport is the reverse mirror dynamic. Instead of pushing the object through space, the system performs a controlled mapping. The object's state, encoded in the envelope, is transferred from Fork A's region to Fork B's region. This is achieved by reassigning the boundary conditions in a higher dimensional configuration space. The process is analogous to a mirror image, but instead of reflection, it's a relocation. What was inside the envelope near Fork A is now inside an equivalent envelope near Fork B, with no classical transit in between. Each quantum tuning fork acts as a high-Q resonator, supporting a set of quantized field modes. These can be electromagnetic, phononic, or even more exotic. The key is that Fork A and Fork B are engineered to have matching mode structures, allowing them to be brought into correlated or entangled quantum states. This enables the manipulation of one fork to influence the state space of the other, forming the backbone of the transport mechanism. The forks are not just hardware, they're the quantum bridges that make non-local transfer possible. The envelope's advanced design is what enables the object to interact with the quantum forks. Built from metamaterials, it can dynamically tune its properties, such as permittivity, permeability, or elastic modulus, to match the resonant modes of the forks. This allows the envelope to act as a programmable interface, encoding the object's macroscopic identity into the field structure. The shell's topological features also provide protection against decoherence, ensuring the object's state remains intact during transfer. For transfer, the object's state, together with the envelope, is encoded into the resonant modes of Fork A. This is achieved through engineered coupling, where the envelope's boundary conditions are mapped onto the fork's quantum field structure. The encoded information is not just a simple signal, it's a complex pattern that captures the object's macroscopic identity. This step is essential for ensuring that the object can be faithfully reconstructed at the destination. The magic of QTF-Transport lies in the non-local correlation between Fork A and Fork B. Through quantum entanglement, or synchronized classical modes, the forks share a joint state. This means that operations performed on Fork A can have immediate correlated effects on Fork B, even across vast distances. This non-local link is what allows the encoded object state to be transferred without traversing the intervening space, echoing the principles of quantum teleportation, but on a macroscopic scale. Unique aspect of the QTF-Transport hypothesis is the idea of dimensional matching. The forks are not just matched in three-dimensional space, they are engineered to have isomorphic high-dimensional configuration manifolds. This means their internal field structures, topological properties, and even extra-dimensional coordinates are aligned. The reverse mirror dynamic operates within this shared manifold, allowing the object's encoded state to be relocated seamlessly from one fork to the other. The transport process begins with the activation phase. Fork A is energized, and the object is sealed within its envelope. Energy pulses from Fork A couple into the envelope's boundary layers, initiating the encoding of the object's state. Scientific labels in the system highlight the coupling of resonant modes and the start of the state transfer process. This phase sets the stage for the reverse mirror dynamic to take over. As the process continues, the object enters the transition phase. Quantum field lines arc between Fork A and Fork B, forming a bridge for the encoded state. The envelope and its contents are now in a state of partial dematerialization at Fork A and partial reconstitution at Fork B. This phase is visually marked by wave contours and directional arrows, illustrating the dimensional handoff that defines the reverse mirror dynamic. In the final stage, the object is fully reconstituted at Fork B. The envelope reforms, and the object's macroscopic state is restored inside the new shell. Residual field lines fade as Fork B stabilizes the reconstructed state, while Fork A dims, signaling the completion of the transfer. This phase confirms the successful redefinition of the object's boundary state, completing the journey without classical motion through space. The envelope shell is a marvel of engineering, combining multiple layers to achieve its function. At its core is the encoding boundary shell, which couples directly to the fork's quantum resonances. Surrounding this is a metamaterial layer that controls wave dispersion and field behavior. The outermost layer is a topological shell, acting as a decoherence insulator to preserve quantum integrity. Each layer plays a critical role in ensuring the object's state can be encoded, transferred, and reconstructed with high fidelity. Detailed look inside fork A and fork B reveals their internal architecture as high-Q resonators. Each fork contains a resonant cavity hosting discrete frequency bands, supported by a lattice structure that shapes spatial mode profiles. The field coupling interface enables interaction with the envelope, while the dimensional manifold adapter bridges internal and external coordinates. Waveform graphs illustrate mode overlap, entanglement potential, and the pathways for encoding and decoding object states. Reverse mirror dynamic is the heart of the QTF-Transport process. It involves a sequence of operations. Fork A's encapsulating envelope integrates into an interdimensional lattice, followed by an X-inversion field handoff along the dimensional manifold. Fork B then receives the capsule and completes the redefinition phase. This mechanism is illustrated with hypothetical dimensional cross-sections, showing reverse field waveforms and the non-traversable space between the forks. Successful transport, fork A and fork B must be perfectly synchronized. The protocol begins with spectral calibration, ensuring both forks share identical mode spectra. Phase locking follows, with reference pulses and feedback loops reducing phase error to near zero. Entanglement channel verification tests correlation fidelity, while a synchronization pulse cascade brings both forks into a unified operational state. Only after pre-transport readiness scans are completed is the system cleared for activation. Forks are embedded in layered configuration manifolds, enabling dimensional matching and transposition. These layers include the ordinary 3D spatial layer, an internal coordinate layer, and a topological layer. Curved grid overlays and mapping arrows trace the object's state across matched manifolds, while scientific labels explain how dimensional matching enables the reverse mirror dynamic. This topology is essential for the seamless relocation of the object's encoded state. Envelope's resonance coupling is achieved through three engineered layers: the encoding boundary layer, the mid-frequency coupling band, and the outer decoherence shield. Each layer is tuned to interact with the fork's resonant modes, ensuring phase stability and minimal decoherence. The coupling interface aligns mode overlap, phase lock resonance pulses, and dimensional coordinates, making sure the object's encoded state is correctly injected into the reverse mirror dynamic. Calibration is critical for the forks to function as a synchronized, entanglement-ready system. The process includes spectral calibration, phase locking, entanglement channel verification, and a synchronization pulse cascade. Each step ensures that fork A and fork B are perfectly matched in frequency, phase, and quantum state, allowing for reliable transfer of the encoded object state. Only after passing all readiness checks is the system activated for transport. When the encoded boundary state arrives at fork B, the fork's resonant manifold stabilizes the incoming pattern. The envelope reforms from the outside inward, first the topological shell, then the metamaterial layer, and finally the encoding boundary shell. The object's macroscopic state is redefined inside the shell, with fork B providing final stabilization pulses. Only after spectral coherence and boundary integrity checks is the object considered fully reconstituted. Dimensional manifold topology consists of multiple layers: the ordinary 3D spatial layer, an internal coordinate layer, a topological layer, and the quantum configuration manifold. These layers provide the structure for dimensional matching, enabling the reverse mirror dynamic and maintaining isomorphism between the forks. The manifold's design is what allows the encoded state to be mapped and relocated across space and dimensions. Reverse mirror dynamic is governed by a set of field equations that describe boundary state inversion, harmonic lattice reversal, and non-local manifold mapping. X-axis inversion symmetry plays a key role, allowing the encoded state to be translated across the dimensional bridge. The output is a reconstitution-ready field packet, prepared for decoding and object reformation at fork. Each quantum fork is a sophisticated piece of hardware, featuring a resonant cavity, lattice prongs, a dimensional manifold adapter, a field coupling interface, and a stabilization pulse emitter. These components work together to support the high-Q resonant modes, enable coupling with the envelope, and provide the necessary pulses for encoding, transfer, and reconstitution of the object's state. A complete QTF transport system integrates all subsystems into a seamless flow: envelope encoding, fork coupling, reverse mirror dynamic, fork B capture, boundary reconstitution, and object stabilization. Each step is carefully engineered to maintain coherence, fidelity, and dimensional alignment, ensuring the object's state is transferred and reconstructed without loss or violation of physical laws. While the QTF transport hypothesis is bold, it faces significant constraints from mainstream physics. Macroscopic quantum state control is far beyond current technology, and the no-cloning and no-signaling theorems limit what can be achieved. Conservation of energy and causality must be respected, and the process must avoid faster-than-light signaling. These constraints ensure the theory remains scientifically grounded, even as it pushes the boundaries of what's possible. There are many open questions for QTF transport. How can macroscopic entanglement be achieved? What are the limits of state encoding and reconstruction? How can decoherence be minimized? And what are the practical engineering challenges? Future research will need to address scalability, fidelity, and the control of higher dimensional manifolds. These questions define the frontier of quantum transport science. Hartman quantum tuning fork transport hypothesis stands as a testament to scientific imagination and disciplined speculation. Authored and articulated by Colonel James Edward Hartman, this theory integrates quantum mechanics, metamaterials, and higher dimensional physics into a unified framework. The legacy of this work lies in its ability to inspire new lines of inquiry and challenge our understanding of space, matter, and information. Summarized, the QTF-Transport hypothesis proposes a method for relocating macroscopic objects using quantum tuning forks and a specialized envelope. The process involves encoding the object's state, transferring it via non-local quantum correlations, and reconstructing it at the destination, all while respecting the fundamental laws of physics. While speculative, this framework opens new possibilities for quantum transport and dimensional engineering. Looking ahead, the QTF-Transport framework invites further exploration into quantum field engineering, advanced metamaterials, and the mathematics of high-dimensional manifolds. Experimental advances in quantum information, entanglement, and topological materials may one day bring aspects of this theory closer to reality. The journey from hypothesis to demonstration will require interdisciplinary collaboration and continued scientific curiosity. Thank you for joining this deep dive into the Hartman quantum tuning fork transport hypothesis. Whether or not the theory is realized in practice, it stands as a bold vision for the future of quantum science. By integrating concepts from quantum mechanics, field theory, and dimensional mathematics, QTF-Transport challenges us to rethink what's possible in the movement of matter and information. Stay curious and keep exploring the frontiers of physics.